Great. Everybody enjoy lunch? Enjoying your day? Awesome. Okay. Um, so here I'm going to talk about tuning G1GC. Has anyone tried to tune it yet? Here. One. How did that work out? Just at the start. Okay, that's good. No one else has tried. Is anyone trying to use G1? Few people. How's that working out? So far, no problem? Yeah. Okay. Well, that's really good, right? Because then you don't need to be here, right? You can go off and work if it's all working, right? And that's basically the message we have here, right? It's like, how do I tune G1GC? Well, I set the max heap size to some appropriate value. And if I don't happen to do that, then of course it's going to be automatically set to be 1/4 physical RAM. And I set the pause time goal, and if I don't set that, then that's 200 milliseconds, the default value. And that's how you tune the G1GC. Any questions? You're all laughing. That's it. That's the presentation. Enjoy your day. Right. Right. So obviously we're all here today because sometimes it's simply not quite that easy, right? So we say, yeah, if only it was that easy, then we'd be okay. Okay, so marketing slide here, so all the techies can turn off for a second. Last year, my CEO said, you realize you tuned about 2,000 JVMs this year? And I said, no, couldn't it be? And it can't be that much. So I went and added up, and I realized that he was wrong, right? But he was wrong because I tuned approximately 3,000 JVMs for trying to move them to G1. For what reason, I don't know. I have no idea why, but that's where it is. And we sort of do this under the brand of JClarity, where we're building what I call the next generation of performance diagnostic tooling or diagnostic engines, and trying to bring predictability into the diagnostic process. And of course, I've co-founded JCrete. If you don't know, this is the hottest unconference on the planet. Yes. Has anyone ever? We have one person who's attended here. Yes. Okay. Yeah. You did test, right? It was hot. Very hot. Yes. And some other stuff and everything like that. So you can Google if you want that one. So as I'm talking to you today, I actually, this is a new thing I just wanted to start talking about. I've been talking about it implicitly for a number of years now. I think I should make it explicit. A lot of the things I do is I just simply build models. And why do I build models? Well, because models help me ignore the complexities of real things, so that I can have a better understanding of how they work, right? And it really helps in a lot of other places too. And in the case of garbage collection, it helps in the sense that it helps you develop a cost model, so you can see what's going on. So if things aren't working right, you can say, okay, well, why? Now I have this model, and I can sort of pump the information into the model, and hopefully it'll provide me some answers, as long as I'm not dealing with the complexities. So if we're going to build a model, then we have to understand what are the important moving parts, or what are the parts in our system that we need to talk about. And I think when we talk about managed memory in a runtime, and this is not just Java, but it's obviously, does anyone see that nice C++ CLR diagram with the garbage collecting units there? It applies to those guys also, right? And you can see there was, like in that chart, it's surely cleared there was a hotspot. Sorry, the JIT was hot for changes, and the garbage collector was hot for changes, and for me that wasn't a surprise, because there's an intricate coupling between these things, because there's more than one moving part here. It's not just collecting memory. We also have to consider that we're consuming memory. And if we're trying to move to a more concurrent model with garbage collectors, which is the trend over time, then we have to look at the the effect that mutations have on the ability of concurrent collectors to actually function, right? So there's three really big parts here. One is allocators, one is mutators, and one is just the act of collecting. So, you know, one allocating, mutating, and collecting. Those are the three steps that we have to consider. And of course, to keep this all consistent, we need barriers, and if we're jitting our code, then of course the JIT comes into play because it needs to insert the barriers all in the right place in order to maintain consistency in our runtime. So that's why I was not surprised to see the JIT and the garbage collector so tightly coupled, because in reality they are very tightly coupled. Right. So we have this seeming battle between allocators versus collectors. And you know, the nice thing about having a collector is that it takes away all the responsibility that we have for managing memory. So we can just allocate, and somehow magically in the background we have an infinite, or as they say in the US, I guess, we have a bottomless amount of memory. We can just keep consuming, and it's really good. But in order to give you this illusion, we have to do something, right? So that's what the garbage collector comes into play. So we can balance the work between the mutators threads that are doing the allocation and the garbage collector by saying, okay, we won't have a garbage collector, so that puts all the responsibility for managing memory on you guys. Or we can take part of that responsibility and automate that, and that's what the garbage collector is for. But at that point, what we want to do is if we put all of the collection work onto the garbage collector, then we're going to end up with really long pause times while the garbage collector does this maintenance step. And we don't like that. Okay? If we go concurrent, then we got another issue because we're modifying memory while we're using memory. And of course, that, you know, if we don't do that right, that can lead to corruption and things like that. So we need to manage that also, right? Which means that if we're going to run the garbage collectors concurrently, then we need to somehow put some of the workload onto the mutator threads. Now, if we put workload onto the mutator threads, of course, we have overhead on the mutator threads, which means our application runs slower, right? If we put all the work in the garbage collector, of course, we have longer pause times as we try to maintain this consistent view of memory. So it means we have to stop everything while we're doing things, right? So those are the battles that we're trying to fight. And in the beginning, we had just a single-threaded stop the world collector, which was basically dump all of the responsibility onto the garbage collector, and you know, the mutators would just go as fast as they can. Of course, we had long pauses because of that. And they said, okay, well, we can shorten that up by parallelizing things, right? That worked for a while. And then we said, okay, so we can start running partially concurrent. And of course, you know, that worked for a while. And then we're saying, okay, well, we need to actually do more to actually try to get more concurrency and try to get, you know, basically more throughput with smaller pause times. So one of the schemes I came up with was G1. Of course, now we're very shortly going to be looking at Shenandoah and Z-GC as being possible replacements for G1 in the future. As I said, you know, the battle on the pause time is continuing, and as it continues, basically we're trying to get these things to be more and more concurrent, but the cost is our allocations, basically our application throughput, our mutations, allocations, and accesses are going to be slightly slower, so it's going to cause us some drag on that end. So let's see what we can figure out, you know, how the G1 fits into all of this. We have things we need. Well, we need to have a Java heap, because that's where we're allocating into. In the case of G1, we're going to take that heap and we're going to divide it up into regions. And we need a collector, so we're going to rely on our trusty mark sweep copy collection algorithm. It's going to be really nice. And we're still going to use this idea generation. So one of the things we used to speed up collectors in the old world was we said, okay, we're going to use this thing known as the weak generational hypothesis. The weak generational hypothesis says data doesn't stay live for a very long period of time. As a matter of fact, most of the data you allocate is no longer useful to the application before it can leave the CPU, right? It's dead. So we can create a nursery, do our allocations there, and we use some sort of copying collector now, and we use a copy collector. We're going to copy the live stuff out to some other place. So that gives you the idea that we have a nursery and we have some other place for copying. And if you think of this as a cost model, so let's go back to cost models and everything like that. So we tend to think of garbage collectors as we're collecting all of the unused memory. Now we've just flipped that over with this particular idea of using generations and copying, because now instead of our cost model being dominated by the amount of memory we have to collect, it's not going to be dominated by the amount of live data that we have. Okay, so in this model, live data is bad. Dead data is good. So as a developer, how can you use that to your advantage? Well, think of it this way, right? If I have globally scoped variables, how long are they going to live? If I have locally scoped variables, how long are they going to live? Right, so what am I going to prefer? Local scoped variables. Yeah, so if you follow that particular idiom, which we know is one of these things that says it leads to other benefits, because how much of a concurrency issue, in terms of concurrency bug issues, do you have with locally scoped variables? Pretty much none. Close to none, if not none. How about with statically globally scoped variables? A lot, right? So you get into this idea that the garbage collector is still there. It's going to support good coding practices. If you follow good coding practices, all of this stuff is just going to magically work for you. If you don't, then of course you end up with a whole host of problems, garbage collection being one of them. Okay. So we have some generational things creeping into this whole notion here. And we have some supporting data structures that we need. We need this thing called a collection set. We'll call it a C set. We need these things called remembered sets, or R sets. We have this thing called an R set refinement queue that we're actually going to use, right? And then once we deal with sorting out what all of those are for, then we can look at possibly how we can get some data out of this thing to tune it. Okay, so we're going to allocate this large heap space in one, or reserve a single contiguous chunk of memory. A JVM startup, and we're going to divide it into approximately 2048 regions. So we'll take your max heap size and we'll do some math on it, and then we'll select a region size which is appropriate to give us approximately that number of regions. So it could be 1, 2, 4, 8, 16 or 32 megabyte region size. Okay, so we're going to end up with something that looks like this. We're going to put all of these regions into a free list. And then this wonderful thing, technology called ergonomics, is going to come along and is going to say, okay, so many of these regions, we're going to say that's our nursery. Okay? Now your application starts. And what does it do? It starts, well, okay, I need to allocate something. So I say new foo. And then what I'm going to do is I'm going to grab a region from the free region list. And then I'm going to start allocating into this as I normally would. So I'm just going to go foo, 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 right? So label it as Eden, start allocating all my objects in it. When I fill up that region, or I hit a waste percentage, then what I'm going to do is I'm going to grab another region, I'm going to refill it, grab, fill, grab, fill, grab, fill. When I hit my allocated number of regions, then I'm going to start what's known as a young generational collection. Now, of course, with the young generational collection, we're going to use our mark sweep algorithm, which is our workhorse algorithm for tracing collectors. And we're going to take this and we're going to parallelize as much as we possibly can. So we're going to break this thing up into things we have to do serially and things we can do in parallel. So one of the first things that we have to do is we're going to have to decide, okay, what are we collecting? So I'm going to take all of the regions, and I'm going to put them into this thing called a C set. And then I need to calculate a root set for the C set. So a root set is going to be all those objects that by definition are live. Now, they may or not be live, but that's a different issue. Okay? So we're going to come up with a definition for what a live object is. And we're going to say, okay, fine, that's external to the C set. It's pointing to something into the C set. We're going to put that into our live object set. And then I'm going to mark everything that's live. And while I'm marking it, I'm going to copy or evacuate that live data to a 2 space. Okay? And then I'm going to put the Eden regions back on the free list. And I'm going to use ergonomics now to recalculate the number of regions to allocate to Eden. And the game starts again. So it's wash, rinse, repeat. Okay? Now, when I build the C set for the next collection, of course, I'm going to put the 2 space regions into the C set. And you end up with something that looks like this. Okay. So when you see these type of diagrams out here, okay, unlike any other diagram you're going to see on G1, they're all wrong. This is correct because these diagrams are actually being drawn from data derived from live systems. All of the other ones are, this is what we could possibly do with G1. So these are sort of imagination. So you're going to see that basically we're allocating Eden from the lower right going up. Now, what happens is that after data has survived a certain number of collections, either 6 or 15, depending upon, it has 2 default values, right? And 15 is actually the max value. So if you start trying to tune the G1 collector, it'll default to 15. So we'll say after 15 collections, the data will actually then start being allocated into tenure space. So I'm not going to evacuate to another 2 space. I'm actually going to evacuate the data that passes the tenuring threshold up into a tenured region. And it starts allocating from the upper left. So that's going to be from the higher addresses down. Okay, so the 2 are going towards each other like this. Right. So let's revisit. So we did a mark sweep, we did a mix of parallel serial phases, place all young gens in the C set, calculate a root set for the C set. So, okay, so now gets into the question, where are the roots for the C set if I'm doing a young generational collection? In other words, where are the pointers that are external to young gen, right? And of course the answer to that is they're in tenured space. Okay, cool. That leaves us with a time complexity issue. In order to scan for roots, I need to go through all of tenured space, and I need to look for things that are pointing into young generational space, right? And this is the problem with the old collectors. The old collectors actually had to do this. We had to scan all of tenured space to find the roots that were pointing into young generational space before we could do a young gen collection, which means that if you look at our cost model, scan for roots is going to dominate, and scan the time complexity for scan for roots is going to be linear to the size of tenured space, which is ick, right? That doesn't scale. That gets us to about 8 gigs, 12 gigs, maybe 16 gigs if we're lucky. I've tuned up to 24 gigs with this strategy, but after that, you know, it's game over. Your pause times are just going to get excessively long, right? Just simply because scan for roots starts to dominate the process and it just takes too long. Okay, so, you know, where are our roots? Well, our roots are up there. So what are we going to do? Well, let's introduce this thing called an R set, a remembered set. And I'm going to lie to you now, so just, you know, I'll tell you this up front. This is not how it actually works. The maths behind this are rather complex, and you don't really need to know it unless you're interested. What we're going to do is I'm going to take each young gen region, and I'm going to create a set of cards for each region that's pointing into the young region, right? So if I have a tenured region pointing into a young region, there's going to be an associated deck of cards. And what I'm going to do is as I mutate, okay, so if I have foo in tenured and I have fa in young, if I say foo equals fa, then what I'm going to do is I'm going to go into that card deck and I'm going to say, okay, well, there's a bit there. I'm going to set that bit, and that bit maps back to that region and that address value. So then basically what I'm doing is I'm recording the pointer value in the bitmap, okay? Now, you think of it this way, right? Every single time your application has to mutate, we're going to have to update the RSet, right? Every time you access, I'm going to have to go through some sort of barrier to make sure all of this is consistent. So, you know, so this is a problem. And it gets even worse because if I'm basically collecting concurrently, then I somehow have to track all of these mutations in a way that I don't disrupt the garbage collector also. So there's a lot of extra work that has to happen in order to maintain this data structure. And we have another problem, right? If we have 2,048 regions, say we have, I don't know, like 500 of them are young gen, and we could have like 1,000 that are tenured, then we have a space complexity issue. And this is why the data structure gets quite complex, and it's quite expensive to update. So we're not actually going to have the mutator thread update. What we're going to do is we're going to queue the information in what's known as an RSet refinement queue, and we're going to have RSet refinement threads working in the background that are basically going to take this data and update the remembered set, right? Before the collector can run, this data structure has to be empty. So they designed it to be zonal. And what they're saying is that I can take the pause time goal. Remember the pause time goal? Yeah, more or less. Yeah. Well, it's 200 milliseconds, right? So basically what I'm going to say is like, okay, well, I know how long it takes me to update. So what I'm going to do is I'm going to try to make the white zone be equivalent to about 10% of the pause time goal. So it's 200 milliseconds. That means I can spend up to 20 milliseconds, draining this queue as part of the collection phases. After that, I'm going to start the remembered set, the RSet refinement threads. And by the time I get down into the red zone, I'm going to say, okay, you're just mutating too fast. What I'm going to do is I'm going to start capturing the allocation threads. I'm going to slow down your application threads by having them participate in the RSet refinement step. Okay, cool. So that covers sort of like the young generational space. So we're going to do a mark copy, or a mark evacuation is what I like to call it, right? And so eventually we're going to, so eventually all of this data is going to end up in tenured, the live data. And eventually tenured is going to get bigger and bigger and bigger and bigger. And when it hits this thing known as an IHOP, which is an initiating heap occupancy percent, you know, if I'm in the US, then I can basically say not the pancake house, if you know what that is. But when you hit the IHOP, and that's about 45% of total heap, then what's going to happen is that I'm going to trigger a concurrent mark of tenured space. There is no sweep, only a mark. Okay? And we're going to try to do as much of this work concurrently as we possibly can. So here's the number of the phases here. I'll just leave them for reading for later. But you can see the red ones are stop the world. The green ones are concurrent. And what I'm going to do is I'm going to mark all of the live data, and in the process I'm going to calculate what's known as an occupancy liveliness factor. Okay? Now, when I build a C set, when this concurrent mark is finished, I'm going to take all of the young generational regions, and I'm going to take some of the tenured regions and put them into the C set. So when the young generational collector does the copying out, it's going to copy out the data out of the tenured regions and put them into new tenured regions. Now, how do we size the C-set? Well, since we know the occupancy percent, we know we can have a rough estimate of how long it's going to take us to evacuate or complete the collection process of each of these regions. We can just select enough of them that are actually going to pad out our time goal. So, here's the number of regions. They have different levels of liveliness. So we'll just sort. You see the two on the left here are empty. They can go back on the free list immediately. On the right, we have things that are really full. So those are going to be expensive because in this scheme, the cost model is, right? It's copy cost. So full is expensive, empty is cheap, obviously, if we're looking at copy cost. If you're looking at the traditional sense of we're collecting garbage, then of course empty would be expensive and full would be cheap. But that's not the case with copying, okay? Which means that we have a number of regions here that are eligible collection. We're going to use this G1 mixed GC live threshold percent flag to set that. Default value right now is currently 85%, which means that anything is more than 85% full, we're just not going to consider it for inclusion in the C-set. Okay, so here's the regions that are eligible. Now, what I'm going to try to do is I'm going to try to complete all of this work within 8 mixed collections. So I'm going to have a young generational collection with an initial mark that's going to trigger the concurrent mark cycle. When the concurrent mark cycle finishes, the next young generational collection is going to be known as a mixed collection. And the mixed collection is going to take a chunk of these regions. And I'm going to have a maximum this is configurable also, but I'm going to have a maximum of 8 different chunks or 8 different mixed collections happening consecutively. Okay, and we can set that. Now, often what you see is that it can do more work, so it's just going to do more work, which means you get fewer mixed collections. I don't really like that because you get a poor work balance in that case. And if it looks at it and says, I'm not going to recover much more memory by collecting more of these regions, then I'm just not going to bother. I'm just going to stop. So there's a waste percentage there. When it hits that percentage, then we're basically finished. So at the end of the day, that's basically how it works. There's really only one more topic to talk about, and that is if we have a 1 meg region, what happens if we allocate an object that's 2 megs in size? Right? That could be a buffer overrun, but of course we've taken care of that, and we're going to call that a humongous allocation. Okay, so here's a nice schematic that shows you pretty much what a humongous allocation looks like. So we have anything bigger than half a region size, and we're going to consider that to be a humongous allocation. So if you look at the coral bits in there, there's 2, 3 coral bits in the middle that are just floating on their own. That's a humongous region start. So that's something that is, if this is a 1 meg region, that's bigger than half a meg, less than 1 meg in allocation size, right? If it's bigger than the size of the region, then I'm going to need humongous region continuations. And so you can see at the top, there is a coral, meaning that's our start. And the rest of the red ones following the coral, that's going to be a continuation. So that's going to be a single allocation, humongous allocation. Obviously, to get the humongous allocation in memory, we need that many contiguous regions. And traditionally, this has been a problem with humongous allocations, is having enough contiguous regions to actually make the whole thing functional, make it work, right? If you don't have enough contiguous regions, you're going to have to force a collection. Traditionally, in previous versions of G1, this has been a full GC. And a full GC is something you definitely want to avoid here. It's very expensive. They're parallelizing it. I think the parallel version is being released as 10 is being released. But even so, that's really not really going to be all that helpful. Much better to avoid the full GCs. So you might ask, okay, so this is where we can actually start doing some analysis. You can look at it. So anybody have any idea what the top humongous allocations might be? Take a guess. Wild guess. Sorry? String literals? Yes, could be. More generically, that would be a... No, metaspace is something different. We're not talking about metaspace today. Byte array, cache. It's a cache in general, something like that. Yeah, string table would be a cache, a form of a cache, right? Byte array could be a form of a cache, right? Okay, so this is one of these things, like a hibernate cache or whatever like that. You create it at the beginning of the application, it stays there in memory, it's stable, it lives, it's fine, right? Okay. What about the things at the bottom down here? Anybody have any idea what they might be? This might be a little harder to guess, but... Sorry? Could be temporary buffers. Most likely in this case it'd be temporary buffers from JSON. Right? Marshalling. Unmarshalling, things like that. Probably that was, I think that was actually the case here, right? Quite often you'll see transitory humongous allocations being a result of what I call marshalling protocols, such as JSON. Okay? So anyway, so if you look at this data, you can sort of get an idea of what's going on inside the application. That's as an aside. When do I have to finish this by anyways? About 1:10 or 2:10? Just for timing. Okay. The nice thing about a humongous allocation is the definition is variable in the sense that it's half the size of a region. So do you know how you can get rid of some of the humongous allocations? Make the regions bigger. Okay. Yeah, I kid you not. But it comes at a cost because updating the remembered sets is nonlinear, and it's nonlinear to the size of the region. So bigger regions mean more expensive remembered set updates costs. It's really kind of like a bit of a problem. And really the worst case condition is if I just simply don't have enough memory, then I'm just going to trigger a full GC. For that reason, it tends to maintain this reserved area in the middle. It's about 10% of total heap. And this here is just simply to try to mitigate having to perform a full GC in order to satisfy a humongous allocation. Okay? That said, here's a newer version of our application. And what you can see in this one is I have dark blue, light blue. Dark blue is occupied, light blue is not occupied space. And you can see that, that these are all tenured regions, and you can see I got a few Eden regions down here in the bottom, but after that, basically all of the stuff filling up memory at the bottom here is tenured regions. So things really can get mixed up really badly. And in this case, you can see I've blown right through the reserved. I pushed, basically Survivor is going to be pushed out to nothing in this case. And if I don't get a collection very shortly, a mixed collection very shortly, basically, this JVM is in serious danger of suffering from a full collection very shortly. Okay? And if you don't have enough room for copying, then that's exactly what will happen, is that you'll end up with a full GC. And we see that quite frequently. Things will just fill up this way. There's enough memory, but yeah, it basically, it's not usable. And in order to make it usable, I need more memory. And so in this case here, we just need to make the heap bigger. There's other overflow conditions that you can solve by taking different techniques, but this one here pretty much is simply make the heap bigger is the answer. Okay, how to get a GC log? Sorry, I didn't get the flags that we use for 9 in here, but for most people, anyone using JDK 9 now in production? 1, 2. Actually, we had to roll back to 8 just recently. So we're at 9, so we had to roll to 8. Which means that we only had like one offending lambda that prevented us from rolling back. It was a take while, right? Anyone been using take while? Guess if you're not in 9, you're not using take while, because take while is it's very useful. Anyways, okay, so if you want to know what the collector is doing, you need to look at a GC log. And so there's some flags, it'll get you some data, and then you can understand what's going on. Now the GC log is this big, long, blobby chunk of text, which is, as I like to say, neither machine nor human readable. Well, most logs fall into that category of being neither machine nor human readable. So which is why I basically wrote something to actually parse this stuff, do some analytics on it, and give us some visualizations on it. So in this case, what I want to do is just say, okay, let's look at a GC log using some tooling here. Lovely. I guess I'll just push this over here because I don't know where any of my things went to. Okay. So here's a GC log that I preloaded. It's from one of our client environments. And you can see we have a number of analytics to make sure, first off, we're getting enough information. Here we're looking for perm space or metaspace triggered collections. In this case, I don't know why we have perm space showing up. I guess it determined it was a log from 7.0, which it shouldn't have been. Oh yeah, in this case it would be. Okay. And again, if perm space fills or metaspace fills or hits the metaspace more correctly, says hits certain thresholds, then that can trigger a collection. And that's something that people often miss. So for the things that people miss or things that people are not as well known, what we're going to do is we're going to throw an analytic up there and basically say, hey, did you realize? And there's a number of other different analytics we have up there that give us proxy measures for things. So we'll pick out, are there calls to system GCs as an example? Oh, here's what's going on with our mixed collections. So in this case, it looks like we could probably do some tuning to get a better balance of mixed collection distribution here. We also look at CPU times. And quite often, well, often enough, we'll get people coming to us and say, we have a pause time problem with our application. We need our pause times to get shortened. And what we'll do is we'll look at these statistics and we'll say, it's not the garbage collector that's the problem. It's your environment or it's something else going on, right? So I can tune your garbage collector for you. It's not going to help you in this case, right? So we'll certainly do it. If you want me to tune your garbage collector, give me a call. I'm quite happy to. But I'm certainly going to tell you if it's going to help or not. So that's some of the things we'll look at. There's more metrics that we have that are not visible right here. But for instance, we can certainly give you indicators as to if and why your system has gone into CPU. So there's some heap too small analytics up there that'll look for things that basically say, your heap is too small, or this data structure is too small. You need to set this flag in order to try to mitigate this particular problem. So here's a view of heap occupancy after the collection, and you can clearly see there's an issue here with this particular log file. First off, the triangle, bluish, purplish triangle things, that's your heap occupancy after a young gen collection. The blue dots are heap occupancy after mixed collections, so you can see how they're clustered. Right, so that's hitting tenured space. We have G1GC cleanup, which is going to report heap sizes, so we're looking at heap sizes after the G1GC cleanup phase, which is part of the concurrent mark cycle. Can anyone see the issue? Yeah, we're consistently losing memory over time, so this could be, this is symptomatic of a memory leak inside the application. It's only 4 hours a log, so it may not be a memory leak. Normally, if I'm going to diagnose a memory leak, I want at least a business cycle of data, which is typically 24 hours, but can be different lengths depending upon the business. So this could still be warm-up. I'm warming up caches and things like that. But in general, I'm going to be concerned that I have heap instability, so potentially a memory leak in this issue. Some of the other useful views here, I'm just going to look at this one here. This one here is going to be memory pool percent sizes. So there's some other conditions that we run into that are a result of the G1 ergonomics deciding to make young space too small. So by default, it can get to 5% of total heap, right, in terms of size. And sometimes that's okay, and sometimes it's just too small. In this case here, it looks like it's 22% in most cases. Well, sometimes it dips down, right? So sometimes we'll just say, don't shrink that much. And that'll clean up a lot of issues, right, in terms of GC frequencies and things like that. So sometimes we can look at that. I don't know how much time we have here, so I'm just going to try to slip through to the more interesting points for this one here. Here's our pause time view. So for G1, actually, this isn't too bad. I mean, for me, it kind of sucks, but it's going to be very difficult to get much better. Well, the way to get better is to not have so much live data. Right. Okay. We have failure events here. There are none. Lovely. I'm going to come down into someone here. We have reference processing times here, right? And you can see sometimes the reference processing times can take up to most of the pause time budget. Actually, if we look at other phase percent, that's all these green dots is reference processing. Parallel reference processing is not on by default. If you have something that looks like this, your easy win might be just to turn on parallel reference processing, right? As a matter of fact, if you look at this, you can see we're processing mostly soft references at the rate of about 50,000 per second. But we also have this trace going up here. So it looks like some soft reference cache thing happening, right? Reference cache happening for weak references. The other reference types seem to be down. So anyways, you can get some ideas as to reference processing inside your application, and that might be an issue. Also, tenuring summary. Here we look at premature promotion. In other words, if data is going to, we don't want data that's going to not be long-lived to end up in tenured space. In this case here, our premature promotion rate is 0%. That's because we've already tuned this thing to get rid of that particular problem. But if we get 40, 50, 30, 40, 50, 60 or higher percentage of premature promotion, that means our young generational space is too small. We need to somehow not let it shrink so much, so we can capture all this this soon-to-be dead data down here. So we do draw out a tenuring distribution curve so that you can see what's going on here, so you can possibly set a tenuring threshold from here. It looks like here 15 is probably the best value because we're still getting good memory recovery. Okay, and if you want to look at the tenuring, the amount of data in tenuring spaces over time, then you can see that's pretty much what it's actually looking like. Okay, so coming back up here, we can see all of the parallel phases and percentage, and we can see that object copy should really be dominating. It should be the dominating phase, but in this case it isn't. There's something else going on. We have external route scanning that seems to be causing a lot of difficulty. I'm not sure why. But if we look at the phases overall, the parallel phase should be dominant. Object copy should be dominant. We don't have that type of dominance, mostly because of the reference processing. And that could be partly due to the external reference scanning that's happening. So the next run I would do for this particular log is I would say, okay, let's redo things. Let's turn on the parallel reference processing first. Let's make everything else seems to be reasonably okay for now, and then let's see the effect that the parallel reference processing has on the whole thing. And if we have if that actually gets to the point where we actually have object copy dominating the picture, then that's a completely different issue. That's essentially it's an unsolvable issue, right? Because if you talk to the G1 guys who are continually working on G1, they're saying they want to get rid of all of the other costs so that generally the only cost that's going to be visible to you is object copy cost. Cool, right? So so the question is, well, if object copy cost is my dominating cost and I still need to do something about it, then what can I do? Well, on the surface, it doesn't look like there's anything you can do. Okay, so the yellow line is the weak generational hypothesis. So it's basically an indication of how much, it's an indication of when data is going to die. And you can see, as I said before, most of it dies early on, and if it stays around, it stays around for a long time. And it only dies when it gets really, really old, or when you shut down the JVM or something like that, right? More importantly, it defines a curve. Okay? And if you have a curve, all of a sudden we have all kinds of maths we can apply at it and apply to it and do things with it, like this wonderful calculus stuff. Does anyone remember calculus? Yeah, okay, sorry to bring it up again. It's depressing, but okay. Yeah, and we can do things like, area under the curve. So what this curve is actually saying is that the amount of data in a stable heap is constant over time for some variable definition of constant. Okay, but basically it's going to stay at that level, which means that if our max heap is the white line, and our allocation is relatively constant, well, it would be over time, then you can see that our garbage collection behavior is going to be fairly constant over time, right? So going back to the cost model, we have a garbage collector that has a fixed cost and a variable cost to it. We can't affect the variable cost because part of the dominating part of the variable cost is object copy, which we've now determined is fixed for each application. Okay, but we do have a fixed cost. So I like this. I use this argument on my wife. It doesn't work, but it's like the vacuuming thing, right? So if I vacuum every day, it takes me like half hour every day. So that's like 2.5 hours a week, or 3.5 hours a week vacuuming. If I vacuum every second day, then that's a lot better, right? Because that's only like 2 hours and 15 minutes of vacuuming a week, or an hour 45 or something like that, right? But you can see if I can get away with vacuuming once a week, then it's only a half hour of vacuuming a week. Yeah, it doesn't work. Okay, but anyways, the point is I can use the same principle here, and in this case, my wife isn't going to argue back with me, right? I can make the heap bigger. If I make the heap bigger, and I'm assuming I get the same allocation rate, what happens to the frequency of the garbage collection? Drops. Which means I'm effectively going to save in the fixed cost because I'm not incurring the fixed cost at a high frequency. Okay? And because the same curve still applies, my variable cost is going to be the same because we determine that's constant for every application. Right? And this works. It's the only thing that I know that works to actually get rid of object copy costs. Slow the collector down. Give it more memory. Right. Yeah, so why is it taking so long? Look at the log. The logs will tell you what's taking so long. You can make the adjustments. Sometimes if you have high allocation rates, you can't tune that out. You got to tune your application. Other times you can look at it and say, I can do something about that. I have an overflow event. I can go and see what that buffer is. I can make that buffer bigger. I can get rid of these failure events, right? I can make sure things don't shrink. So there's all kinds of different configurations I can use in order to try to get rid of whatever problem the GC log is telling me that I actually have. Okay. So, did you like Sensa? It's cool? Cool. So my boss Slacked me this morning and said, okay, we need more GC9 logs for testing. If you have a GC9 log, send it to us. We can get you a free license for Sensa. Okay? So you just go to jclarity.com and, well, you send me a GC log or whatever at support@jclarity.com and just let me know, and we will flip the license at you. For performance tuning workshops, I have it at my CodeWorks site, and if you want to know more about our tooling, then you go to jclarity. And now that's really the end, so now we can really, I don't know if we have time for questions, but if I'll take one or two. Yes. Oh, no, you're saying we don't have time? Oh, okay. Oh, sorry. Yes. Thank you for attending this talk. And no, no, really, seriously, thank you. You've been great. And any questions, I'll take them. Yes, sir. We had a customer that needed us to be in Java 8. And it was just easier for us to roll everything back than just to do a one-off for him. So since they were giving us enough money to do it, we said, okay, we'll just roll back. Right? But it means that we can go to, we compile with Java 8, Java 9, we'll compile with 10. So it's like, you know, not a big deal. Interesting question. Yeah, it's money. We're not immune to that effect, unfortunately. Okay. Any other questions? Yes, sir. They're automatically put into a humongous region. The humongous regions, as you can see from the views that I had, were always going to be allocated in tenured space. If you turn on region liveliness info, I guess is the flag, and you'll get this data dumped. I have a project on GitHub in my GitHub account called GC Viewer thingy. Anyways, that creates these charts, so you can visualize that data coming from the GC logs in that case. Any other questions? Yes? Ah, right. I didn't mention C4 collector Azul. You know, the Azul guys are very, 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 very clever. Probably some of the smartest guys I know. Their collector is good enough that GC pause times aren't really an issue. Operating system stalls, virtualization stalls, and other kernel maintenance things actually are a bigger issue than the pause times you get from the Azul C4 collector. So in that way, I think it's quite brilliant. That said, I think that what we're seeing with Shenandoah, and I don't know about ZGC yet, because you know, that's been basically a phantom thing that hit us from left field. We can see that there's really been a war on pause, you know, this pause time thing, and the collectors are running a lot more concurrently than they have been, which means that the commercial value in C4 has basically been reduced over time. And like I said, the Azul guys are very, 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 very clever. They planned for this a number of years ago, which means that they've been investing in JIT technologies and just in, you know, ahead of time and just-in-time compilation techniques and compilation preservation techniques and things like that that are actually, again, giving them really, really good value for going, if you want to go towards a really high-quality commercial JVM. It's certainly the way to go. C4 was the argument yesterday. I think within 2 to 3 years, C4 won't be the reason, but there will be plenty of other reasons to go in that direction. Yeah, but I think I'm guessing we're about 2-3 years off of Shenandoah being able to be used in production. I have no idea about ZGC. Oracle claims, but you know, it's like the perpetual motion machine. Only the inventor is doing it. Okay. Yes.
Does Sensum have a suggestion report telling you might
We
try this and this and this?
we did, but our customers took it as you must, and so we've pulled them out. But we've had paused. But in live, we actually have a version that'll do batching. So if you want to look at, I don't know, like 200 or 300 JVM GC logs at a time, you know, we can manage that quite nicely, and we can monitor live. In the live systems, we did have a pause time prediction thing, which means we could give you like a 30-second. We can give you up to 30 seconds heads up. You're about to have a long GC pause. right? And we had that approximately 90% accurate, right? Which is pretty accurate, but it gives you 1 in 10 false positives, which people don't like. You know, in other words, they want you to be perfect all the time, but you know, this is probabilistic stuff. So, yeah, I mean, if you don't mind being wrong, I'm quite happy to put them back in. We don't always get it right, in other words. Right. I mean, tuning a collector, first off, we only ever do it in production environments. Second, you never get it right the first time, right? Because these are emergent systems. And there's a feedback loop with your application between the application and the garbage collector. Which means that you need to do it once, figure out what the feedback loop looks like, do it again. You'll probably get a better idea what the feedback loop looks like. And by the third time, you're going to get it right. But sometimes it might take a fourth or fifth, depending if you hadn't gone far enough, right? But this is why the predictions are wrong, because it's not that they're wrong, it's the first step. You need to keep going. But people don't want to keep going. They just want it all in the first step. But it doesn't work that way. Okay? So if you don't mind us being wrong, well, I'm happy to put them back in, but people are complaining about us being wrong, so we had to take them out. Or say we may be wrong, I guess would have been better. Okay. Any other questions then? Awesome. Then I will wrap it up and let you go to the next talk. Have a good one, guys. Cheers there.